Welcome to the second part of the seminary, where I will be talking about, I will try to introduce very briefly, the high-resolution TEM imaging, scanning TEM, and some analytical techniques. Starting with the high-resolution TEM, let me remind you that we are now in this situation in which, with the help of an objective aperture, we select, together with the transmitted beam, several diffracted beams. So we use all of them to create an image. We are now talking about phase contrast. The typical point resolution is around 2 angstrom. Magnification range is above 200,000 times. And this time we are able to obtain atomic structural information about crystalline materials, also information about the atomic structure of extended structural defects, such as dislocations when observed hand-on. Okay, or structural information at the atomic level about the planar defects, interfaces, also when observed edge-on, or about 3D defects, precipitates. Moreover, we can obtain quantitative structural information at nanometric scale by measuring the strain fields, by mapping the strain fields associated to these defects. We are talking about the phase contrast in TEM, in high resolution TEM. This is because a high resolution TEM image is nothing else but the interference of all the selected beams, the direct beam and the diffracted beams. So any variation, any phase variation in between these beams leads to a modification in the interference conditions and in the image that we observe. So let's describe very briefly the mechanism which supports the formation of images in high resolution TEM mode. So it all comes to find the relation between the electron wave leaving the sample until it gets to the image plane of the objective lens. So I have defined here the terms that we are working on. We work with the incident and the emerging electron wave. We have a transfer function associated to the sample. We operate with different operators in order to describe the propagation of the electron wave in the free space between the different components, different lenses in the microscope. And we have another operator associated to the action of the lenses onto the electron beam. Okay. So in this case, we operate with the convolution. In this case, we operate with the multiplication. This is the way the electron wave looks like, the intensity distribution of the electron wave looks like in the back focal plane of the the objective lens. It's nothing else but a Fourier transform of the exit wave, the electron wave leaving the sample. So this is the relationship between the object and the intensity distribution in the back focal plane. So we have a Fourier transform. Now if we add the influence of the objective lens, meaning that the objective lens have a finite size to which we associate a function like this, and like all the lenses in the optical system and electromagnetic systems, electron microscopes. Also, the objective lens is affected by aberrations, which produce a phase factor intervening in the shape of the electron wave in the backfocal plane of the objective lens. We come to this formula, which includes the Fourier transform operated by the objective lens, the contribution of the finite size of the objective lens, and the contribution of the aberrations. Going further to the image plane, we will end up with we will convolute with the propagator between the focal plane and the image plane, and we finally get this kind of expression between the electron wave in the image plane with respect to the electron wave at the exit phase of the sample. So you see that we have a convolution with the function t, which is defined as the transfer function of the microscope, of the objective lens, actually. And this is the general mathematical formula of the contrast transfer function, which includes all the mentioned contributions, where here I have explicitated all the possible aberrations influencing the shape of this function. Why is this function important? Because you can see the microscope as a filter, as a band pass filter. So this is the shape of this complicated function. It's a representation in the reciprocal space for different values of delta f. Delta f being defocus of the objective lens, which intervenes at this level here. So you can notice that simply by slightly modifying the defocus of the objective lens, we change the shape of the contrast transfer function, and by changing the shape, it means that we allow only certain spatial frequencies to cross, to be transmitted by the objective lens. And namely, it's about the spatial frequencies contained under the envelope of this function. So you can imagine that spatial frequencies situated in this region here are very low, very poorly transmitted by the objective lens. And there is a certain observation condition, certain defocus values, which is named Scherzer defocus, which generates this particular shape of the contrast transfer function, which means that the function reaches its broadest range, allowing for the transmission of spatial frequencies. So this is the defocus allowing to get the most of high resolution of lattice information about the sample that we are observing. What about the exit wave, the electron wave at the exit of the exit phase of the sample? Let me remind you that we are talking about thin samples. Thin samples are considered samples that act only on the phase of the electron beam, not on its amplitude or its intensity. So these objects are known as weak phase objects, and in this case the exit wave can be approximated with this formula, where phi represents the projected potential. which means the atomic electric potential integrated along the sample thickness, along Z. Along Z from 0 to the sample thickness. So high resolution TEM image can be correctly interpreted only if we are in situations where the sample works as a weak phase object. So for very thin samples, the correct interpretation of the HRTEM images is only done with the help of image simulation software. And this software is based on this condition of weak phase object. So it's applicable only to very thin samples, and I suggested here values like tens of nanometers. A few examples of high resolution images from the sample that we have seen earlier in conventional TEM imaging. Now, at a higher magnification, we are capable to see the atomic structure of the sample in the substrate, the first deposited layer and the second deposited layer. The contrast is not perhaps the best. Anyway, here is the interface between the two, and here is between the strontium glutinate substrate. And in order to correctly interpret, understand what is the physical meaning of the bright dots that we see in these high resolution images, which are, as I told you at the beginning, maxima of interference between diffracted beams, we need to perform image simulation, because at a slightly variation of the observation condition, namely the objective lens defocus, you can obtain a totally reverse contrast. So you, in order to be sure that what we see here is a column of atoms or is the space between columns of atoms, you have to perform image simulation, and in doing that you have to reproduce as much as possible the observation conditions that you have used while you were at the microscope. I mean, the same values of defocus, the same values of other parameters characterizing the microscope, like different aberrations which have not been corrected, like astigmatism, or well, astigmatism it should be corrected, but spherical aberration in our case, for example, in the microscope in Bucharest. Well, there is another unknown here, which is the thickness of our sample. You will never have precise information about the local thickness of the sample as the beam crosses it, because all you see is a projection. You have to turn the sample at 90 degrees to see what is the real thickness in it. So that's why usually we perform a simulation generating series of images obtained for different values of objective lens defocus and sample thickness. And we approximate the generated simulated images, we fit them to the experimental images, and this is how, more or less, we get an information which is as precise as possible and as correct as possible with respect to the experimental image. This is another example of image simulated for this interface of strontium titanate and strontium glutinate, and the generated images for different values of sample thickness. Another example of the defect that we have seen a few minutes ago in conventional TEM, this time at a higher magnification we can examine edge-on defects, and you have it here. And this is the crystal structure of silicon in the perfect part of the crystal, and this is the defect induced by hydrogen
exposure to hydrogen, to plasma of hydrogen. So we see that these are 1-1-1 planes in silicon. So we see that, and it was exactly the same information that we had obtained by conventional TEM. I mean the nature of the planar defect that was a 1-1-1 plane. Only this time we can see it at a high resolution, and we can try to model the atomic structure of this defect by testing different possible models, which are then simulated. This is a set of simulated images for this kind of structural model of this defect, which has then been inserted into the experimental image, and seen that, and we deduced that this could be an appropriate structural model compared to all the others suggested theoretically by Muto in this paper. Another example of a dislocation observed in high resolution imaging, a dislocation which is seen end on. So this is the structural model of an edge dislocation. The edge dislocation is the line that goes into the screen now, limiting this supplementary crystal plane. We have such a dislocation here. It's not very easy to notice, to observe it. You can do it easily by tilting. This is how we used to do some time ago when we were still working on with photographic images, with photographic recording of the images. So we were just looking at the high resolution images at the grazing incidence, and this is how we could identify the position of the dislocation. Nowadays, with the help of a computer, you can do it more easily by performing fast Fourier filtering, and you can get this kind of image on a computer. And indeed, this was here we had a perfect 60 degrees edge dislocation in cubic boron nitride. Although we cannot see it, we can find the information about the Burgers vector by building a Burgers circuit around the dislocation, and we clearly see the closure defect here, and this way find what is the Burgers vector associated to this dislocation. Something about scanning transmission electron microscope. We are in yet another configuration of our instrument. This time the beam is not parallel as we were for TEM and HRTM. Now the beam is focused into a tiny spot onto the surface of our sample, and then it is scanned across the sample, and on the other side of the sample we detect, with the help of an annular detector, the beam, the electron beam, the electrons scattered incoherently or coherently, but mostly incoherently, by each atom in the sample, in the position of the beam. We can also collect the electrons scattered at a low angle around the optical axis of the microscope using another detector, and this is how we get two kinds of STEM images: annular dark field images, or ADF images, or bright field images. What kind of information we can obtain by STEM? Now we are talking about mass thickness contrast. It's not diffraction contrast, it's not phase contrast, it's mass thickness. It's affected by the atomic number Z and the thickness of the sample in the precise position of the electron beam. We can obtain, in case we have an aberration corrector, resolutions as low as a few picometers, in between 5 to 8 picometers. Our microscope has proven this 8 picometers resolution with this, with the aberration corrector that we have installed on it. We are working at much higher magnifications. What we can obtain as information is also structural information at atomic level of crystalline materials. We can obtain, of course, structural information at atomic level about interfaces, extended defects, dislocations, planar defects, precipitates. But we can benefit also greatly by this Z contrast, the mass thickness contrast, which can help us to intuitively identify atomic species in our microscope. So this is the formula of the scattering cross-section depending on the Z square, so mass contrast. Here we have an example of such images obtained in STEM mode, 2 different images, dark field image and bright field image, obtained with 2 different detectors. So using this Z square dependence of the contrast in the dark field image, we can surely say that the brightest spots correspond to heavier atoms with larger Z, while softer spots are correspond to atomic species with a lower Z. So in this case, we are at the interface between BTO, barium titanate, and strontium ruthenate. So in the barium titanate part, we can surely say that these intense bright spots are barium columns of barium atoms, and the softer spots belong to titanium, which has a lower Z. In strontium ruthenate, the difference is not that obvious between the Z. So on the image itself, you cannot directly say, but we can trace, as you will see, some line profiles, and we can intensity profiles, and we can easily identify. The bright field image is somehow the opposite of the dark field image. So in this case, the darker spots, which here were bright spots, correspond to the heavier atoms, and the softer spots correspond to titanium atoms. But we can do more. I mean, if we are able to somehow collect the atoms, the electrons scattered at a very low angle, close to the optical axis of the electron microscope, we are in the so-called annular bright field condition. And in this case, we can collect and observe the electrons scattered by the softest atoms, the oxygen atoms in our case. So here on these images, the small dark dots are nothing else but atomic columns of oxygen. So here in this image we have all the information about all the different types of atomic species in our sample. Well, this is a particular situation, because this structure, this particular structure of a perovskite, in this particular orientation along the cubic axis of the perovskite, allows you to obtain pure columns of barium, pure columns of titanium, and pure columns of oxygen. If you tilt the specimen and go to another crystallographic orientation, you will get columns, atomic columns, but this time you will have a mixture of atoms along the atomic columns. And you will not be so sure in assigning these spots to a certain atomic species. Now, as I told you, we are in a very particular condition. But this is an example to show you what is, for some situation is right, the power of this method. Here we are at the interface between PZT and strontium rutenite. And as I told you, we can benefit from the Z dependence of the scattering cross-section, and to determine what is the physical nature, what is the nature of the atomic planes which are in contact at the interface, which is the atomic plane at the end of the strontium rutenate and which is the atomic plane at the beginning of the PZT layer. Only by judging the line, by looking at the line profile associated to this Z-square variation. So you can, by analyzing this contrast, you can come to the conclusion that the strontium rutenate layer ends up with the strontium oxygen layer, while the PZT layer starts with the zirconium titanium oxygen layer. So this in different situations can be very useful in further describing the, let's say, the electrical properties of such a junction between two materials, and also judging by the gradient of the intensities in the interface region compared to the rest of the crystal on each side of the interface. We could estimate that we have some kind of atomic interdiffusion across a band of about 7 atomic planes around the interface. This is an image just for a simple curiosity to show that CS-corrected TEM imaging is able to image even single atoms. And this is the case of a nanoparticle of gold. And if we, in processing the image, if we oversaturate the image, we can see that next to the nanoparticle, we have tiny dots, which are nothing else but isolated gold atoms, which have the proper diameter of about 1.4 angstrom. So again, this is not a perhaps not a very practical situation, but just for curiosity to show again what is the power of this kind of microscopy once you have corrected this spherical aberration. Something about the analytical techniques in TEM. There are two that we use, two techniques. First of all, energy dispersive X-ray spectroscopy, and I have figurated here the mechanism which it's at the base of this analytical technique. So of course we have an incident beam, the excitation of an internal electron layer, and the de-excitation of the atomic species resulting with the emission of an X-ray photon, which is detected with the help of a detector and further analyzed with the computer, displayed as a spectrum. We can perform qualitative and quantitative analysis to identify the atomic species present in our sample and their proportions. We can, of course, couple the analytical technique with some observation with imaging technique, the STM, and we can get very local chemical information. In our case, we have a space resolution of about 1 nanometer. I'm sure that on your microscope you will be able to obtain atomic resolution information, again on very particular samples, due to the fact that you have a much better detector than we have. But anyway, this kind of imaging, coupling chemical analytical and imaging techniques allows us to obtain the so-called data cubes containing both image and chemical information, which you can further process and obtain offline information about local composition in your sample by extracting different spectra from different locations and performing local quantitative analysis. The Eels technique is illustrated here. This time we are not interested about emerging secondary or secondary radiation emitted by the atom under the influence of an incident electron, but we are interested on the fate of the incident electron after interacting with the atom in our sample. In the fact is that after this inelastic interaction, in which a part of the incident of the energy of an incident electron is offered to the atom in the sample to produce some excitation or ionization, and this we can measure the loss of energy with the help of a spectrometer. First of all, we have to disperse the electrons coming from the sample with the help of a magnetic prism, and then the dispersed beam is recorded with the help of a detector and displayed as a spectrum. This kind of, again, we can couple this analytical spectroscopic technique with the imaging mode in STEM. This time we can couple also with the imaging mode in TEM to obtain chemical maps. In our case, where we have a aberration corrector on the STEM mode, we can obtain these kind of chemical maps at an atomic resolution. Again, in very particular situations, and this is an example on strontium titanate. This is a chemical map obtained in this square here, based on a spectrum like this. Well, this is just a raw spectrum, but while selecting some features associated to strontium, titanium, or oxygen, we are able to generate filtered images which are nothing else but chemical maps of strontium, of titanium, and of oxygen at an atomic resolution, and we can overlap all these three maps into a single one and to get a situation of how all the atoms are distributed with respect to each other in the crystal in that particular orientation. Another example of an application of this spectrum imaging across an interface in the strontium rutenate barium titanate interface. Again, if we perform the line profile across the interface, we have this oscillation of intensity, and we can associate the maxima to the higher Z and the minima to the lower Z titanium in barium titanate here, which is very obvious, let's say, less obvious here in the strontium rutenate, because we have a lower difference between the atomic number of the two elements. But we can perform atomic chemical mapping at the interface using this time Eels and not EDS. And this is a spectrum image obtained at the interface. This is the interface region. And here what you see are local spectra, Eel spectra, extracted from this single atom, column of atoms corresponding to titanium, and we see that we have only the titanium. This spectrum belongs to barium and has been extracted from this here. This is a spectrum extracted at the interface,
and this one is extracted from the strontium here. It's a very low signal to background and signal to noise ratio here, but this is the theoretical position of strontium, and this is the amplitude of the strontium signal here in this position. So by processing this, by extracting the chemical maps associating to these spectral features, we get these chemical maps associated to titanium, to oxygen, to barium, and to strontium, and we can overlap them in order to come to a conclusion regarding what we have at the interface, because by simply judging the line profile here, we were not quite able to see and to conclude what is the nature, for example, of this atomic plane here. Is it barium, is it strontium, or ruthenium? So this kind of elemental mapping allows us to see that, to say that indeed we have a mixture of strontium and of barium at the interface, not only strontium or barium. So we have a local interdiffusion at the interface. And with that I will conclude, and I will thank you very much for your attention.